You know, I was sitting in front of my monitor late last night just staring at a chunk of code I'd written, and I had this weird, almost existential moment. I mean, I'm typing these English words while return, if, void.
Right, and throwing in some punctuation.
Exactly, a curly brace here, a semicolon there. And somehow this inanimate slab of silicon and metal just understands it. It executes logic. It feels like magic.
It really is the closest thing we have to actual incantations. You speak a spell in text, and, well, the golem obeys.
Yeah.
Usually.
Usually being the heavy lifter in that sentence. But here's the thing that always trips me up when I stop to really think about it.
Yeah.
The computer doesn't actually know English. It doesn't know what a variable is or a loop. To the machine, that source code file is just a long, messy, chaotic stream of characters. It's just W, then A, then I, then E, then E. It's just noise.
Exactly. It's a raw stream of bytes. It has no structure, no meaning, no intent. And that is exactly where we are starting today. We are answering that fundamental question. How does the machine go from that noise to structure? How does a computer actually read?
So we are doing a deep dive today into lexical analysis, or as it's more commonly known, in the trenches, scanning.
Right.
We're pulling from the Class 5 notes, the slide deck on scanning, and we're going to be referencing Chapter 3 of the Introduction to Compilers and Language Design textbook pretty heavily.
This is effectively the first contact moment in the compiler pipeline. It's where the rubber meets the road. If you don't get this part right, nothing else matters.
So let's lay the groundwork. If we zoom out and look at the big picture, I'm thinking of figure 2.2 in the notes, the stages of a Unix compiler. Where exactly are we standing in this whole process?
Imagine an assembly line. At the very start, you have a hopper dumping raw materials onto the conveyor belt.
Okay.
That material is your character stream. That's the .c file or .java file you just saved. That stream flows immediately into the first station, the scanner.
And the scanner's job is just to organize that mess.
Precisely. The scanner takes that raw stream of characters, which is just a sequence of ASCII or Unicode values, and chunks them into meaningful groups called tokens.
Okay.
It then hands those tokens off to the next station, the parser.
You know, I've heard a lot of developers, and I'll be honest, myself included, ask why we can't just skip the scanner.
Sure.
The parser is where the heavy lifting happens, right? That's where the syntax trees get built. The structure lives there. Why can't the parser just read the file directly? Why do we need this middleman?
Think of it like reading a novel. When you read a sentence, your brain doesn't process THE. You don't consciously process individual letters.
Right.
Your brain automatically groups them into the word the. If you had to consciously assemble every single word from its letters while simultaneously trying to understand the plot, your brain would just overheat.
So the scanner is basically doing cognitive load balancing for the compiler?
That's a great way to put it. It's a translator. It converts spelling into vocabulary, and it removes the noise, the white space, the comments, so the parser doesn't have to deal with garbage. I mean, if the parser had to worry about whether there are 2 spaces or 3 spaces between keywords, the logic for the parser would be impossibly complex. You can't build a house on a swamp.
So the scanner drains the swamp first.
It drains the swamp so the parser has solid ground to build on.
I love that image, draining the swamp of characters. So, okay, if the scanner's output is these tokens, we really need to get our definitions locked down tight. There's a distinction in the notes that I think trips up a lot of people.
Oh, yeah.
The difference between a lexem and a token.
Yes. And in casual conversation, we swap them all the time. But in compiler design, they are legally distinct. If you mix them up, you're going to have a hard time understanding how the data actually moves.
Okay, let's break it down. Let's start with the lexem.
The lexem is the tangible thing. It's the raw paint on the canvas. It's the specific sequence of characters you actually typed in the file.
So if I type counter,
then the string of characters, COUNTER, is the lexeme. If you type the number 42, the characters 4 and 2 are the lexeme. If you type a plus sign, the plus character itself is the lexeme.
Okay, so the lexeme is the instance. It's the physical reality of the code in the text file. So then what is a token?
The token is the label. It's the abstract category. When the scanner sees the lexeme 42, it doesn't just pass 42 to the parser. It packages it up and stamps it with the token INTLite, short for integer literal.
So the parser doesn't necessarily care what the number is at that exact moment. It just needs to know, hey, a number goes here.
Exactly. And this is the key insight from the slides. It's a one-to-many relationship. There's one token type called ident for identifier.
Right.
But that one token maps to an infinite number of potential lexemes. X, Y, my super cool variable, temp. They're all different lexems, but they're all the same token type.
That makes so much sense. The parser writes a rule like, if I see an ident followed by an asygnot followed by an intil, it doesn't write a rule for if I see X followed by 100.
Correct. That would be impossible. The token provides that abstraction layer.
But isn't the relationship sometimes one-to-one?
Yes, specifically for keywords.
Yeah.
Take while. The lexem is WHILE. The token is just while. You can't use while as a variable name in C or Java. It's reserved, so that mapping is totally unique.
The lexem while always results in the token while.
Always.
Okay, so lexem is the specifics, token is the category. Now this seems simple conceptually, but making a machine do this sounds hard.
It can be.
The machine reads character by character, COU. How does it know when it's finished a word? How does it know count isn't actually the start of counter?
That is the million-dollar question, and it comes down to pattern matching. The scanner is essentially a pattern recognition engine. We define shapes that we expect. An integer looks like a digit, followed by more digits, and the machine watches for those shapes.
And in the notes, it mentions regular expressions, or regex.
Right. We use regex to describe the patterns mathematically. It's a concise language for describing sets of strings, but you can't just code a mathematical formula into the CPU.
Right, you have to implement it.
And to do that, we use something that sounds very sci-fi, finite automata.
Finite automata. It sounds like a villain in a cyberpunk movie. The finite automata are coming for your data.
It's much less threatening, I promise. Think of it as a board game or a flowchart. You have a bunch of circles drawn on a page. We call these states, and you have arrows connecting them.
Okay, paint the picture for me. I'm the computer, I'm the scanner, I'm reading a file.
Okay, let's walk through it. You start at the start state. It's a blank slate. You read the first character. Let's say it's a letter, I.
Got it.
The diagram has an arrow labeled letter pointing to a new state. You follow it. Now you are in the identifier state.
Okay, I'm in the identifier state. I'm excited. I read the next character. It's F.
The identifier state has an arrow looping back to itself saying, if you see another letter or a digit, stay here.
Yeah.
So you stay. Now you have collected if.
Okay. I read the next character, and it's a space.
Ah. Now the identifier state looks at its arrows. It sees no arrow for space that keeps the pattern going. So it says, I'm done. It hits what we call an accepting state.
And it ships it off.
It takes the bundle if, checks if it's a special keyword, which it is, and emits the IF token. Then it resets to the start state to read the next thing.
So it's basically a state machine that just walks through the text, eating characters until it hits a wall, then bundles them up and ships them out.
That's it. That is the heartbeat of the scanner. Loop, consume, accept, emit, repeat.
But wait, code is messy. It's not always that clean. The notes bring up this concept of ambiguity. This feels like where things could go wrong.
Oh yeah, ambiguity is the bane of the scanner's existence. It happens when one sequence of characters could, effectively start two different valid patterns.
The notes mention the look-ahead problem.
Right, a classic example, the greater than symbol. The scanner reads A2. It enters a state where it thinks, okay, this is a greater than operator.
Logical, it's a valid token.
But in many languages is also the first half of greater than or equal to. So the scanner can't just declare victory yet. If it emits the token immediately, it might be wrong.
It has to peek at the next character.
It has to predict the future, basically.
Yeah.
It peaks. If the next character is an equal sign, it consumes it and says, aha, this is a GEOP. If the next character is anything else, it stops and says, okay, it was just greater than.
So the rule is to be, what, greedy?
Yes, the scanner must be greedy. This is formally called the maximal munch rule.
Maximal munch. She sounds like a cereal brand.
It does. But the rule is, the scanner keeps eating characters as long as they form a valid prefix of a token. It wants the longest possible match. It will always choose over just if it can.
That sounds like it creates a lot of work. Peeking, maybe backtracking if it gets it wrong.
It does. We call it redundant coding. The scanner's doing extra checks constantly. But we accept this trade-off because it makes the language readable for us, for humans. We want to write.
We don't want some weird single character for it.
Exactly. We could design a language to make the scanner's life easier, but it would be a nightmare for us to write in.
So we make the machine sweat so we don't have to. I can get behind that philosophy.
That is the essence of high-level programming. We abstract the complexity away from the human and pile it onto the compiler.
Now, speaking of making things easy for humans, let's talk about what the scanner destroys. We said it's a gatekeeper, what gets left on the cutting room floor.
White space and comments. And this is a really important conceptual shift for new compiler writers.
Because as a developer, I spend a lot of time on my comments. I write detailed explanations of why I'm doing something. I organize my code with nice indentations so it's readable.
And the scanner obliterates all of it.
Gone.
To the parser, your comments simply do not exist. They are stripped out completely.
That's kind of a lonely thought. The logic is stripped of the programmer's personality.
In a way, yes. The scanner sanitizes the input. It turns your expressive, indented, commented code into a dry, flat stream of tokens. If, lparen, ident, lt, intlit, rparen. That's all parser sees. It doesn't see your joke in the comments.
Surely it keeps something. If I get an error, the compiler tells me error on line 14. If the scanner threw away the new lines, how does it know it's line 14?
Excellent point. The scanner doesn't just strip and forget. It preserves metadata. While it's chewing through the white space, it's counting the new lines. It attaches that line number to the token structure.
Okay, that makes sense. So every token knows where it came from.
Exactly. And there's one more crucial thing the scanner helps build. The symbol table.
Right, the address book for the code.
Yep. When the scanner encounters a new identifier, like a variable name myCount, it doesn't just pass the generic ident token. It often takes that string myCount and creates an entry in a side database called the symbol table.
It's like planting a flag.
Exactly. It says, I saw the string myCount. Later, the parser and the semantic analyzer will fill in the details about what myCount actually is. Is it an integer, a function? But the scanner initiates that record.
So it's not just a shredder, it's a filing clerk. It shreds the garbage but files the important names.
Precisely. It separates the signal from the noise.
Okay, so we've got the theory, we've got the circles and arrows. How do we actually code this? Because looking at the notes, there's a big warning. Don't write a separate if statement for every letter.
Please, for the love of efficient code, do not do that.
Mm-hmm.
I've seen students try to write scanners with massive switch statements for every single ASCII character. It's unmaintainable and just slow.
So how do we optimize the state machine then?
We use character classes. Instead of transitioning on specific characters, we group them. We define a class called letter, which includes A through Z and A through Z. We define digit.
So the state machine logic simplifies to, if I see anything in the letter bucket, go to the identifier state.
Exactly. It collapses the complexity of the diagram immensely. You aren't checking for A or B or C. You're just checking, is it a letter?
And what about the actual reading of the file? The slides mention a function, getchar.
And getchar is the workhorse.
Yep.
You don't want to just raw read from the disk every single time you need a letter. That's incredibly slow. Getchar usually handles buffering. It grabs a chunk of the file, holds it in memory, and just hands the scanner one character at a time.
And it probably skips the spaces too, right?
Yeah, it usually handles the dirty work of silently skipping the spaces and tabs so the main scanner logic doesn't have to worry about them.
It's so interesting how modular this is. The scanner asks getchar for a letter. The parser asks the scanner for a token. It's like a bucket brigade.
That's the beauty of compiler design. It's separation of concerns at its finest. Each component has one job, and it does it blindly.
Now, I can hear some of our listeners, maybe the ones who just want to build React apps, asking, why do I care? I'm never going to write a compiler.
I hear that a lot. But understanding scanning makes you a strictly better programmer. First off, regex. If you understand how a scanner consumes input, you become a wizard at regular expressions.
Which is useful for, well, everything. Data validation, searching log files.
Exactly. If you know maximal munch, you understand why your regex is grabbing too much text. Second, debugging. Ever had a silent syntax error? You forget a space between a variable and a keyword, like return X instead of return X.
And the compiler throws some weird error about an undefined symbol instead of a missing space.
Yeah, right. If you understand scanning, you know immediately, oh, the scanner grabbed return X as a single identifier because it was greedy, it didn't see the keyword return. You stop seeing magic and start seeing the mechanism.
You know how the machine thinks.
You do. And finally, tools. If you ever want to write a syntax highlighter for VS Code or a code formatter like Prettier or a linter,
you're building a scanner.
Congratulations, you are building a scanner. You are parsing text into tokens to color them or rearrange them. It's everywhere.
All right, let's pivot to the practicals. We have deadlines looming for the class. What's on the radar?
Okay, immediate tasks first.
Journal entry for week 2. That's due this Sunday, February 1st.
And I want to reiterate the 2-1 rule. The professors are strict on this.
Remind us what that is again?
You need a minimum of 2 paragraphs of reflection. Not just, I did the reading, but here is what I struggled with, here is what clicked. And this is the part everyone forgets. You must include one question.
A genuine question.
A genuine question. Ask about something you didn't understand, or a what-if scenario. What happens if the scanner hits a null byte in the middle of a string?
Yeah.
If you don't include the question, you lose points. It's the easiest point to lose.
Got it. 2 paragraphs, 1 question. Now, the big one. The lab.
This is where things get real. Reference Appendix A in the text. You're going to construct a scanner for the B minor language.
B minor. Sounds musical. Is it a full language?
It's a teaching language designed specifically for this course. It looks a lot like C, but stripped down. Don't let that fool you. The scanner you build has to be robust.
What are the stumbling blocks we should look out for?
Strings. Strings are notoriously difficult. You have to handle quotes inside of quotes. You have to handle escape characters, like when you type N for a new line.
Right. Your scanner sees a backslash and an N, but it needs to turn that into a single new line character.
Exactly. If you mess that up, your string parsing breaks completely. And comments. You need to ensure your scanner correctly identifies and discards everything in between, even if it spans multiple lines.
Okay, now there's a very specific policy regarding this lab in the syllabus, the LLM policy. We are using a tool called BitBuddy.
This is critical. The course is treating AI not as a cheating tool, but as a research subject. You have 3 modes, and you have to lock in your decision before you start the lab.
Let's run through them. Mode 1 is I've got this.
That means manual coding. No AI generation, just you and the documentation. You're required to do at least 2 exercises in each lab this way.
Mode 2, vibe coding.
I love that name. This is the collaborative mode. You can leverage the LLM, modify the prompts, manually edit the code it gives you. You work with the AI, but, and this is key, you have to attribute what is yours and what is the AI's.
And mode 3, you do it.
This is the prompt engineering challenge. The AI generates everything. You can refine the prompt, but you are not allowed to manually fix the code.
Wait, so if the AI misses a semicolon, I can't just type it in?
No, you have to tell the AI, you missed a semicolon on line 42, fix it.
That sounds incredibly frustrating.
It's an exercise in precision communication. It teaches you how to direct an LLM, which is a skill in itself.
The journal.
The journal is all you, no AI. That is your human reflection.
Understood. So pick your mode, manage your BitBuddy, and watch out for those string escape sequences. So, to wrap this up, we've successfully turned a stream of messy characters into a clean stream of meaningful tokens. We've separated lexems from tokens, tackled ambiguity with greedy matching, and we've mercilessly discarded all the user's comments.
We have prepared the ground for the parser to do its work.
But I want to leave everyone with a thought today. We talked about how the scanner throws away comments and whitespace because they don't matter to the logic.
Right.
But those things matter to us. They carry the intent of the programmer.
That's true. The comment explains why the code exists. The code only shows how.
So if the computer throws away the why, does the machine actually read your code? Or is it only reading the structure of your instructions?
It's a deep question. If the scanner removes the context, the meaning of the program, the soul of it is lost to the machine. It's just following orders.
So where does the meaning actually live then?
Well, technically. That's a problem for semantic analysis.
Always another layer.
Always.
That's a deep dive for another day. Until then, look at your code a little differently. It's not just lines of text. It's a pile of lexems just waiting to be categorized.
Thanks for listening to The Deep Dive.
Happy scanning.